Hi, everybody. Welcome to our webinar today on central heat pumps. I'm Joe Wachunas with Electrify Now. I'm here with my teammate, as always, Brian Stewart. We've got a great presentation today. We have two panelists who will introduce shortly, Christopher Diamond and Zach Turner. We would love for you all to share where you are coming in from today. Go ahead and put it in the chat room. We'd love to hear where our guests are from if you feel comfortable. So go ahead and throw that in the chat room. And speaking of chat, real quick, folks, feel free to use the chat throughout today's webinar. Put in your comments. If you have a question, it's easier to track them in the Q&A. So if you can keep your questions in the Q&A and use the chat for comments, that would be great. Thanks. We are Electrify Now. If this is your first time seeing one of our webinars, we try to boil down our message into 4 clear points to help folks decarbonize their lives. Number 1 is clean up your electricity supply. That's through solar on your roof, signing up for community solar or your utilities renewable program. And then electrify your home. We've got a lot of webinars on our YouTube page. Just Google Electrify Now YouTube to teach you all the ways. And today we're going to be talking about an important way to electrify your home. Electrify your ride, be it your car or your bike. Make it electric and clean up your ride. And then electrify everyone is the 4th step, and we'll talk about that in just a second. We want to say thank you to our Electrify Coalition members, over 40 members strong, and we want to give a special shout out to our new member, Climate Solutions, who just joined. If you're interested in joining the Electrify Coalition, please email Brian or I afterwards, and we can put our emails in the chat room. A huge thank you to everyone. We just tallied it up, and just through our webinars alone last year, we raised $3,700 for the Electrify Everyone program. For those of you not familiar, this is where Electrify Now partners with the nonprofit Community Energy Project, and we raise money so that we can replace old gas polluting hot water heaters with new efficient heat pump water heaters. They save both carbon emissions and hundreds of dollars a year for folks. So we really appreciate everyone who's donated and continues to donate to our program. Great. So a quick plug for our upcoming Electrify webinars. Next month, we're going to be taking a look at clean hydrogen with a very prestigious professor from Cornell on blue versus green hydrogen. Lot to talk about on how hydrogen can be clean or not. And then in March, we're going to be repeating our sequestration week. If you all remember from last year, we devote a whole week to talking about carbon sequestration because it's going to be really important in decarbonizing and keeping our climate livable. So we're going to have a webinar every day for 5 days of sequestration week. Then in April on Earth Week, we're going to be talking about carbon offsets and doing a deep dive on those. And then in May, we're going to be talking about clean electricity, different like geothermal and coal, lots to talk about in May. So you'll find it on our website all the time, electrifynow.net, and we also will send you an email, hopefully not too many. Great, so Brian, what are we focusing on today?
Well, we're focusing on heat pumps, and I like to start really high level here for everyone just until we get to we're going to get down to the nitty gritty. But let's start high level for just a second. And why are we even talking about heat pumps in the first place? And a lot of people don't really appreciate the impact that fossil gas, methane, natural gas, branded natural gas. A lot of people don't appreciate the impact that fossil gas has on our environment. And if you look at the numbers, approximately 25% of our U.S. emissions come from burning natural gas for heat. This is not the natural gas that's used for electricity. We're just talking about the fossil gas that's used for heating our homes and buildings and other end uses. And as we learn more about how much of this is actually leaking into the environment, many times purposely by the fossil fuels companies, we see that the impact of methane starts to approach the impact that coal has in terms of its negative impacts on the environment. So a lot of us have grown up with this idea that natural gas is clean and clean burning, but there's more and more evidence to the contrary almost every day. The other thing that I think people really don't have a good understanding of is how much carbon emissions are produced from heating our homes with natural gas. I mean, most people have a pretty good idea about automobiles, and part of that is because it's a real visceral process. When you go to the gas station, you're connecting your car to this pipe full of gas. You smell it. You know where it comes from. And when you fire up your car, you see that cloud of smoke that comes out of the back. You can smell that too. And so it's really clear that there's carbon emissions happening with your automobile. With your house, it's kind of the same situation. The fuel is coming from some of these same places where we get our gasoline, but it's underground. You don't really see it. You don't connect to it every day. When you turn on your devices in your home, particularly your furnaces and your water heaters, you don't are even aware of the flame, and you don't see the smoke coming out of the smokes, the roof. So it's just not as obvious. But in truth, it's almost double the impact that an automobile has in terms of its carbon emissions. And again, these numbers are going to vary really widely depending on the size of your house, how well insulated it is, how new your appliances are, et cetera. But this range of 5 to 11 tons is pretty good range for here in the Northwest in terms of how much energy we use for heating our homes. And it's not that different around the country, to be honest. If you're in a really cold climate, it could be higher. The big culprits in our homes, so to speak, are our gas furnace and our gas water heaters. Today, we're going to be talking about furnaces, and that's where the big opportunity is for us to kind of take a whack out of our home emissions. And the solution is heat pumps, which we talked about before. And a lot of people, we're going to talk a lot more about heat pumps, but the science behind it can be complicated. But I like to just point out that these things, as magical as they seem, are very familiar to us. All of us have had refrigerators in our lives for our whole lives since we were little kids. Air conditioners are also heat pumps in a way, but this technology has been around for a long time. And one of the way that heat pump works is it moves heat from one place to another. So your kitchen is getting slightly warmer in order to take all the heat out of your refrigerator and dump it into your kitchen, basically. But a lot of you will have experienced this exact thing, that on a hot day, particularly if you don't have air conditioning in your home, like think back to last summer during the heat dome, a lot of people were experiencing kitchen temperatures, over 80 degrees inside your kitchen. But still, your refrigerator is making ice. So that just shows you the power of this technology, that it can really operate with these huge temperature differentials and create these huge temperature differentials. So it's creating ice in a hot climate, and the opposite can also be true. You can create heat when it's very cold outside, and we'll be talking more about that. All right. There's basically two types of heat pumps: the central ones that are connected to ducts, and then ductless ones are called mini splits. Today, mostly, we're going to be talking about these central systems, but there's some really interesting combinations that are possible too, and we'll be touching on that later. So this is roughly what we're going to try to touch on today: why heat pumps can improve your comfort and reduce carbon emissions. We're going to be talking about the differences between ducted and ductless, like I was just showing. We'll go in more detail on that. We're going to be talking about different types of ducted systems, and also how you might even combine a heat pump with gas furnace or replace it for an all-electric system. There's an important thing that we have to talk about, which is your house, because a house that's poorly insulated is not going to work well, or maybe your ducts don't work. So we're going to talk a little bit about that. And hopefully through this, you will really get a sense of the key things you need to know if you're thinking about installing a system in your home. All right, so we've got two great guest panelists today, starting with Christopher Diamond from Northwest Energy Efficiency Alliance. He's the co-founder of the Heat Pump Coalition, which is a group of almost, I think it's over 250 North American energy efficiency professionals that are working to accelerate the market adoption of heat pumps. And his research focuses primarily on variable speed heat pumps, and he'll be talking a lot about that today for space heating and cooling. And his background is he's got a master's degree in building systems engineering and over 25 years of experience in energy efficiency and solar engineering, solar energy technologies. And then we'll also be joined by Zach Turner. He's a comfort advisor for climate control. He's been in the industry for 12 years, and he really, I think you'll get a sense of this, how he takes this home as a systems approach to help homeowners choose the right HVAC equipment to suit their needs. And I think you'll also get a sense of how he appreciates the flexibility that this new generation of high-performance heat pumps gives homeowners to address really common health and comfort issues. And so he is going to be coming at this from the really practical side of having installed a lot of these systems in the past. And together, between these two panelists, I think we've got, couldn't ask for a better overview of the technologies. All right, with that, I'm going to turn it over to Christopher, and we'll dive into things.
Great. All right. Thanks, Brian. Thanks, Joe. All All right, we're going to dive right into this. We've got a lot of content to cover, and I'm eager to share. Make sure I've got the presentation we've got set up. I'm just going to cover the basics and some technology and types. And then Zach's going to dive into a little bit about finding your home sweet spot, what's appropriate for your house, how to think about your house as a whole system. We're not going to be talking a whole lot about the types of systems that are more appropriate for homes with baseboard or radiant floor or wood stoves. Though I'm going to mention some of those details. Right off, the basics, I think it's kind of useful to sort of point out what is the typical average Northwest energy use. This is for an average home in the Oregon, Washington, Idaho, Montana area. As the little pie graph shows to the right, it's important just to realize that about half of your total energy use is for the heating, ventilating, and air conditioning, or HVAC, of your house. So that's about a quarter of your total greenhouse gas emissions come right out of this area we're going to be talking about. Electricity use in the Northwest is about 12,000 kilowatt hours. Gas about 720 therms per year. Cost is roughly $1,800. These are averages. There's a big range of variation between small houses and big houses, old houses and new houses, homes in Montana versus maybe Tacoma, Washington. So your mileage will vary. As Brian pointed out, these things are well known. They behave a lot more like pumps than they are energy creators. They don't actually create heat. All they do is move it, just like a water pump. And kind of at the core of all this is this refrigeration cycle, which your refrigerator has. And all it's doing is using a little electrical power to move heat energy from the cold location into the warm location. And that is why you need to add electricity in the refrigeration cycle, because you're kind of going against the normal flow of heat moving from hot to cold, which doesn't require any mechanical assistance. But we're moving heat out of cold air, and there is plenty of heat content in cold air, into the house during the heating season, or we can reverse that and move it from inside the house to the outside in the summer, and that's called air conditioning. This slide here I'm showing has a key metric that we use commonly, which is called the coefficient of performance. And that really is just a measure of the ratio of how much energy you're getting delivered into the space divided by the amount of energy you're purchasing. So heat pumps tend to get somewhere between 2 and 5. 3 is a pretty common number. For every 1 unit of electricity you buy, you're going to move 2, so you get a total of 3 into the new location. All right, so why heat pumps? Why are we all interested in, why have I dedicated my recent career into this whole idea? Well, there are 5 primary value propositions around heat pumps: comfort, cooling, carbon reduction. They are very customizable. They are very suitable for lots of different applications, and they can be very cost effective for serving unique needs of each individual house. This graph on the right is one that kind of compares the relative pounds of CO2 equivalent per million BTU delivered into a house of some kind of typical archetypes: a gas furnace, an electric furnace, an old single speed style heat pump, or the current new best heat pumps. And as you can see, it's not just the amount of CO2 from the natural gas source, but also a relative contribution for if there's any methane in the system or refrigerant leaks in the case of heat pumps. So on total balance, the current worst case solution is electric furnaces, especially here in the Northwest. And that's what I'm primarily working on. I'm trying to figure out how to get electric furnaces switched over to variable speed heat pumps. And I work for the Northwest Energy Efficiency Alliance. We're a nonprofit that serves 150 plus Northwest gas and electric utilities. We're completely fuel neutral, and we like efficiency on all scales. So I just wanted to be very clear and upfront about that. All right, let's take a look a little bit at the relative cost and carbon comparison of different types of home heating systems. This is just looking at heating. And the orange item, that's the electric furnace. That's what I'm really focused on. I'm also interested in switching out old heat pumps into new best technology heat pumps. And you can kind of see that the top above the line is how much you spend per million BTU delivered into a house. A typical house uses somewhere between 30 and 50 million BTUs per heating season in the Northwest. And the below the line is showing the carbon footprint or carbon equivalent footprint of these. To kind of get a gauge, it's not just one metric we're using to consider what's the right heating system. All the blue items are some kind of combustion heating system, and we're going to be talking about a handful of these. This page here is just in case you want to go back and take a look at this power plant and PowerPoint and see any of the definitions and words we're using. I'm skipping over it. No need to read that detail. It's just there for reference. Next, I'm going to talk a little bit about the technologies and types. There's really two primary technologies we're dealing with right now. We might call the conventional single speed or single stage and dual stage. These fall into the category of constant speed. And that's kind of like your refrigerator. It operates at one speed. The new variety are these variable speed machines that you're hearing about, ductless heat pumps, mini splits. Those kind of fall into two categories of design for more moderate climate and those designed for colder climate. And I'm going to show you this graph here because it's really valuable to kind of point out one of the key things about heat pumps is that their heating ability, or their cooling capability for that matter, decreases as the temperature difference increases. So for heating, the amount of a heat pump can actually heat the house diminishes as it gets colder and colder. This graph here shows outdoor air temperature on the x-axis, and on the y-axis is the amount of heat. The red line shows what your house needs. And you can see as it gets warmer and warmer, your house needs less and less heat. By the time it reaches 65, just your own body heat and your appliances and your various electronics in your house is plenty to keep the house warm during the daytime. So that's what your house needs to stay at a nice livable temperature. When we talk about a single stage heat pump, the green line here kind of shows how the capacity begins to decrease over as it gets colder and colder. And at some point, it reaches this crossing point where the heat pump is unable to meet and maintain the house temperature. So if it kept going colder and colder, the heat pump wouldn't be able to maintain the house temperature. Typically at this point, an HVAC contractor will disable the heat pump and switch it over to electric resistance heating, which was that very large carbon footprint that we showed earlier, and which is primarily why I'm really interested in these variable speeds. A variable speed has a much wider range of operation. And this particular blue line is actually a cold climate line, and there's a variety of different curves that fit somewhere between single and variable. So this is sort of the worst case and the best case kind of range of operation. But the main point is that the variable speed heat pump has an operational range that's much wider than the older single stage heat pumps. And this is important because we have different types of climates. So I got 4 climates here, and I'm just kind of illustrating in these graphs what is the heating and cooling weighted hours. So this is not just the number of hours, but multiply the hour times how much heat is needed for these different climates. And the big tall bumps, these are the heating bumps, if you will, that kind of larger bump for Portland. And the smaller one, that's the amount of heat that needs to be moved out of your house for cooling to maintain cooling temperature. And so now I'm going to overlay what the range of these different types of heat pumps are in the heating season. And you can see really clearly that these variable speeds actually now can achieve space heating capabilities for almost all these climates, except for maybe Bozeman, where it actually gets cold enough that even a variable speed heat pump needs some form of backup heat. But certainly in Portland, the variable speed is more than capable. If you're in California, a single speed or a dual speed is more than capable of meeting the heating load, but there are other reasons maybe to consider a variable speed heat pump. So are variable speed heat pumps really worth it? That's a question I kind of commonly hear from my colleagues and folks I talk to. Um, on a simple cost basis, they have about the same life cycle cost as a single speed or a dual speed. Variable speed heat pumps cost a little more, but they have lower operating costs because they use less energy. The key differentiator, as I see it, really comes down to they're able to operate quieter. They provide more stable temperature because they're not going on and off. They're operating at whatever speed is necessary to maintain just the amount of heat you need for your space, heating or cooling needs. And the third primary reason to consider variable speed heat pumps is that they're actually able to operate when it's cold out. And I mean, really quite cold out. The constant speed's primary advantage, though, is clear. They have lower first cost. And one of the drawbacks comes down to you're going to have some form of backup heat in most climates. So we're going to be talking about some of the configurations, but principally we're focused on, as Brian pointed out, just the split system central forced air. There are other variants of these kinds of heat pumps, and we're probably room for another presentation some other time. You may have seen the ductless mini split. They commonly have an outdoor unit, which is a little box on a pad, and some form of indoor head. Refrigerant lines connected to and move the heat back and forth between the two machines, and a controller is used to set the thermostat. This is a very conventional, we call ductless mini split, or DHP, and it's commonly a single indoor, single outdoor configuration. There are new, more sophisticated varieties of these that are multi-head mini splits, where you can have more than one outdoor units with multiple indoor units. And these indoor units can take lots of different form factors. They can be ceiling cassettes, or little short duct air handlers, or even floor-mounted varieties. They're great at providing really unique zonal heating solutions, and Zach's going to talk a little bit about that. One of the things that I always caution people about is that because they all have the capability of providing lots of heat in every room, it's really easy to oversize and put more than you need in a house with multi-splits. The main thing we're really talking about is the central forced air systems, and that really comes down to that box in your garage or your closet or somewhere in your house. Maybe it's up in your attic space. This is called the indoor air handler, and it consists of typically a fan in a box plus some kind of heat transfer component that's, in the case of a heat pump, it looks like a radiator coil from a car. If it's a furnace, it's got some kind of combustion heat exchanger. And the outdoor unit. For heat pumps, these are the three typical form factors. There's sort of the classic air conditioner style vertical discharge square boxy one. There are these side discharge larger varieties, and there are these varieties that are principally used with small mini splits, and they're just physically smaller. So that's the kind of thing you're going to see when you're talking about a heat pump in your house, an outdoor and an indoor component with a refrigeration line. But there's another component that most people don't really address immediately when they think of a heating system, and that is your house. Your house is part of the HVAC system. Its amount of heat loss or gain through the amount of insulation or what kind of windows you have, or if you've got air infiltration, leakage into your house. All homes have some form or some measure of air leakage, some way more than needed. There's also heat loss distribution, the ductwork, if it's in a crawl space or in a basement or in the attic. All these have impacts on the total system design and where it's located. Lastly, to point out is that each room is going to have a different need. And you might think that small rooms need little heat or cool, and big rooms need more heat and more cool. And that's generally true, but you can certainly have a small room with a very big heating or cooling need if it's got lots of windows or infiltration, or a very large room that doesn't need hardly any heating or cooling if it's surrounded by other rooms or well insulated, good windows. So that kind of first stage of kind of understanding what your house is about is kind of where we're going to go to next and what Zach is going to talk about. So with that, I'm going to hand it over to Zach. Take it away.
Thanks so much, Christopher. And thanks, Joe and Brian, for having me. So this picture is to show basically where I typically come into the process. Most of the time, I'm the guy that comes out when whatever was there prior is not working. So people aren't really thinking about this whole range of options. They're thinking, you know, can I have heat tomorrow? When can you get here? Hopefully this perspective, my experience, will allow me to share some real practical tips about how to think about this and if a central heat pump system can be a good option for your house. So in general, right, we as HVAC contractors have dedicated a lot of our lives to installing these fossil fuel burning plants into people's basements. I say this, I want you to be mindful, you know, a lot of us are very invested in combustion, and we're used to working with this 3,000 degree blast of heat. And now, you know, many of us are all, this morning I was in a training event and I was heartened that so many were really talking about central heat pumps and all the advantages. But beware of who you're talking to and getting advice from. I want you to think about this 3,000 degrees versus soaking up that energy that's around your house to use as heating source, because I think just having this picture in your mind as we discuss further will help in some thinking about how to design your system appropriately. The discussion is usually driven by this fear of not having enough heat, right? You're investing in a system and the goal is to be warm. And certainly it's an HVAC contractor's nightmare to get a call after the fact. Hey, you put this new system in and it's not doing what we expected it to. And the important thing to point out here is something that feels really contrary. And that is that it's not a bigger is better scenario. In fact, what's most often happening is that the equipment is oversized and often vastly oversized. And a lot of times the ductwork is undersized, or the heat's just not getting to where it needs to go for whatever reason. I think of, you know, all these situations where I go out and somebody's system has died and I bring these temporary little 5,000 BTU space heaters. So just think your electric Home Depot heater to tide people over. And when I come back a few days later to do the install, people are not huddled, freezing in the corner. And I'm not advocating that kind of heater. I'm just saying that much smaller systems, it's indicative that they're going to work really well for people. So really, I want to be thinking about how we're delivering superior comfort. And that comes down to delivering the right amount of heat to the right place at the right time. We want to have this control. So steady heat at more modest temperatures allows for more even temperatures, better control of the system, usually some mixing so that we have less of a differential and maybe upstairs, downstairs. So the system, the advantages are twofold. They're on the comfort side and certainly on reducing your energy use. I have this picture of the stove here. To me, it was kind of a fun example to show that there are not actual controls over the different burners. They're just on, off. There's not even like low, medium, or high, or 1 through 10. It's just this stove, you're trying to cook with it, but you can only turn it off or on. And you really have no control. And that's the way we're often heating our homes. Another example. Sorry.
Go ahead.
Just taking a shower is more comfortable than having a bucket of hot water poured over your head. Both deliver the same amount of heat. So modern equipment is modulating and variable speed and important to comfort. So that's the point of the picture on the bottom right, is to keep this guy comfortable, right? So to Christopher's point earlier, and I want people to keep in mind that blast of the burner versus absorbing heat, and we're trying to condition these spaces. And if the heat is just going right out, say through leaky can lights or whatever, then you can, let's have a look at the next slide. The leaky house, same thing for leaky ducts. And my goodness, this is so common. I really go under so many houses, and sometimes it looks like, sometimes it's great like that on the left, or even that picture on the bottom right looks pretty good to me, but I still go through them and will find totally disconnected ductwork. So our average is over 25% loss. It's pretty major.
Yeah, and it's commonly lost in locations that you don't really want heat, like the attic or the crawl space.
That brings in a whole other subject of air quality, where it's pulling in air from all the nastiest places. Yeah. So another factor is just undersized or crimped ducts. And again, just picture those two delivery, two modes of heat or temperatures that we're working with. I have on the bottom left a picture of a snorkel, just to keep in mind that it matters how long the runs are, how big those runs are, and just the analogy of a common garden hose, and just some common sense about getting the temperatures to where we want them. So how do we put the piece, make a diagnosis based on this set of all these information inputs? First of all, look, go into the crawl space or the attics. If the existing system works, and turn it on and see. I have some nice digital tools to measure airflow, but if you also just take a sheet of paper around, you can feel in different rooms where you have airflow or don't. As a homeowner, you have the best experience of your home, and you'll know a lot of this just from living in the space. It's really interesting. We can do a lot looking at your energy bills, and we can compare that to weather data. Now, this is getting a little bit more in depth, but it is important to be really trying to make the decision based on some information. And so the point I was making earlier about so many HVAC contractors just coming in and working with what they're used to, or thinking about things with rules of thumb and grossly oversizing systems. There's a lot of information about the house from when it was built or last had a major remodel. We feed all of this into to make a thermal model. We should be putting it all in the computer, or and it's a thermal model of the house. That's called a manual J load calculation. And then you have real data about what the heating and cooling needs of that. You can do a block load, that's the whole house. But usually, to Christopher's point earlier, we can be looking at it room by room, and we'll be putting in things like, how many windows there are, or the orientation of the space. And there is another level to this, right? Because the data is only, the results you get are only as good as the data that you put in. So if you have a difficult house, or you have what I call hi-fi taste, meaning you just really want to make sure that you get a beautiful result, then you have to put in real inputs, which could require some testing. So that means testing the house with a blower door, or testing if your ducts are leaking with a duct blaster, possibly using some thermal imaging. So some really cool tools to get to zoom in on this picture and get some real data to work with, or about what you need on the house side.
Yeah, and Zach, I might just simply state that if your house is built after the 1992, 95 kind of range on the West Coast of the US, you've got a pretty energy efficient construction. They certainly got better after that, but pre-1990s is where homes had much less insulation and were substantially less. So that's a nice dividing line to kind of think, if I've got a pre-1995 home, I might want to consult with my local utility and see if I can get an energy assessment of my house. And they might be able to help out with having someone come and assess whether or not there are some insulation or window or air sealing improvements that might be valuable. This is if you have the time and $300 to $500 to pay for an energy assessment to be done in your house. It's certainly well worth it.
So thank you. Yes. Once you have the data about your house, that's on the top right, I just have, these pie charts. It will tell you what, how many BTUs you should need for heating, or maybe your tonnage for cooling. I'd say be data driven, right? All of this equipment we're talking about today has charts like that bottom lower chart. They will say what Christopher was describing earlier, at what point they deliver the amount of heat, and you're going to be matching that up to your climate. There is wonderful information that should be part of this discussion. And it's easy to focus on, just the rating of a single piece of equipment. And I have a picture on the bottom right that just says AHRI matched equipment. The point there is that it doesn't really matter what rating, what possible capacity an individual component of the system has. What you really want to keep focused on is how that equipment will work together with the other piece of equipment that it will work with. And then you have to work with somebody who understands, how that heat will be distributed. If the ducts are appropriate, and the whole house is a system now, even considering the home. This slide just starts with the most common equipment that I see. And so, probably, most of the time I go into the house, we have on that right, the furnace, and that box is called a coil. That's the thing that has a radiator in it, and our condensers on the left, which every year those have to get more efficient. And the way they do that is get more surface area. In general, those pieces of equipment are growing. So if you have, 20-year-old AC unit that you're looking to maybe replace with a heat pump, you need to think about that footprint and think about it having, their giant radiators. Their purpose in life is to move a lot of air, so it needs to have 3 foot of clearance in front of it and room around it. It can take a lot of space that you want to keep in mind. So that could be your outdoor component combined with a traditional coil, or it could be a situation where we're not doing any gas and we have a box that looks like the furnace. It just has the control and the fan in it, and of course the coil, but no gas burner. And nowadays that can be a beautiful heating system. So that heat pump does the work inside, can grab the heat or send the heat out. And perhaps there's times when that combination doesn't cover the whole load, but that heat strip, basically like a toaster or a hair dryer electric element in there, can make up the difference. So those are the most common scenarios, but I just want to point out that these mini split outdoor units, which have some real advantages. They are physically so much smaller. They tend to be, in general, the side discharge units options are much quieter, so that's important for comfort. But the mini split outdoor units tend to be quiet, and they are the inverter driven, meaning they have the variable speed and they handle that range nicely. A lot of these mini split outdoor units, they work beautifully at they can give a lot of heat at a pretty low outdoor temperatures. So some nice advantages to these small units, and especially keeping in mind that so much equipment is oversized. There are systems where we have an air handler that it's just a one-to-one. Now we're using them. It's called a ducted mini split, But really what it is that outdoor unit coupled with the box on the right, a mini split air handler, just replaces a furnace. And it will a lot of times be the same cost as a furnace AC system, but now you've got a furnace and heat pump. And excuse me, you have an air handler, a replacement of your furnace. You've got an air handler that will do a really nice job, but you have this outdoor unit that's so much easier to place. There's one other interesting variation that we can do recently is there's this little interface. It's a 24-volt interface that takes input from a regular thermostat. So maybe you've got your Nest or Ecobee or whatever thermostat you already like. And it will allow you to put together a traditional furnace coil combination and use that small mini split heat pump as your outdoor unit. And so, you know, a lot of times you can run that outdoor unit and it can cover your whole load. And even so, it may be a lot easier physically to do the replacement to a furnace, but you can just use it as an air handler. Sorry, I missed one point on that last slide. Is if you are using that mini split heat pump with the air handler, now you're in the world of mini splits. So you could potentially use a connection, multi-port mini split and replace a furnace, but maybe you have an upstairs with terrible airflow where it's going to be really hard to add cooling. So you might do, you know, one other head on that outdoor unit. And so you replace your furnace with the air handler, but you do one additional mini split head to serve an upstairs room, so it also has cooling. Or maybe you have an addition that has lousy airflow. And so again, more flexibility. So to come up with cost-effective central heat pump options, here are just some questions to think of and keep in mind the different, the temperatures that you're working with. How much of your current system can be used? Will smaller equipment work? And usually, absolutely. Could we simplify your system? Maybe even get rid of backup, which is something I do very often for my clients. And I follow up and make sure that they're happy and warm, and they are. So considering the first cost versus that cost to operate, and then all these wonderful non-monetary benefits, because I'm doing my load calcs with the aim of delivering better comfort. And it's certainly wonderful when you can lower your energy use and carbon footprint. So I'd just like to finish with an example on the next slide of my own house. So here is a 70,000 BTU, a pretty good size furnace, 80% old style that I got rid of and replaced it with a new variable speed heat pump. Now I did put a furnace in place because I had some other reasons that I wanted to try it, but I didn't turn it on. I actually run 100% on the heat pump. And we recently had a week of, it was getting down to 20 degrees, and we were so much more comfortable with this new system than with our old system. It was a wonderful change, and it was also nice that it kept exactly to, we like it pretty warm in our house, and it handled the load just fine. Now, in making this switch, in our household, we've achieved a 54% reduction in our energy use. It's a 29% reduction in utility costs, and it looks like we'll be saving over 7 tons of carbon each year. So hopefully that was some good practical information that's helpful to people.
Okay, well, I want to give you guys a little summary of kind of the different options and put together a little table that I want to share with you. This is going to take a little bit to get through. How are we doing on time? Looks like we got enough time. I've laid out a table here that kind of shows 5 high efficiency variants and 5 sort of what I would call low efficiency variants. And we've been talking a little bit about the ones that have been principally for homes that already have a gas furnace. That's what Zach was focusing primarily on. And if you have a gas furnace initially, you might have a choice of keeping the gas furnace, go get a high efficiency gas furnace with a good air conditioner, or you might choose to do a dual fuel solution like Zach put into his house, but he didn't turn on the gas. That's an unusual step taken, but it certainly works. And you can combine those with mini splits. Zach, you didn't put a mini split with yours. You did the full variable speed heat pump, as I recall. Is that right? So the other variants that I talked about a little bit earlier, which is replacing the central gas furnace with either a variable speed heat pump designed for moderate climates or a variable speed heat pump designed specifically for cold climates. And that's really just sort of a where do you physically live? And the one area we didn't cover a whole lot was the multi-head, and that's because they're generally not used for homes unless they're homes that have like baseboard heating or really bad ductwork. So if you've got an existing heat pump or an electric furnace, your energy efficient option is to upgrade to a variable speed heat pump. They are a little more expensive, but as I pointed out, that's sort of on balance is sort of cost neutral over the lifespan. The main advantages comes from all the comfort and distribution and such. If you've got a baseboard heated house or your ducts are really poor, you might consider going with a multi-head split system. If your ducts can be sealed and repaired, then your whole suite of options are back and open to you. And I kind of have down here in the low efficiency section some more common conventional kind of solutions that are out in the market. And you can really see just sort of the relative impact of cost versus operating. All these things kind of they're rough approximations. If, for example, you are in a high electricity cost area, say California, the heat pump operating costs would probably be $2 signs rather than 1, but I'm referencing this as to the Pacific Northwest. So that's the kind of core comparison of different solutions on a cost, operating costs, and carbon basis. Zach, do you want to add anything to this description before I go on to our final summary?
Thank you, Christopher. I'm just starting to look over the chats and the many questions that are.
I mean, I guess I do love this. This is kind of like a great summary in terms of just everything we sort of talked about. And I do want to point out that, this, I think you can see here that one of the things is just a reality that in general, if you pay more for the system up front, you're going to have lower operating costs. Or you can go for a cheaper system, but you're going to have really high operating costs. And so that's why I think the sticker shock can be a real thing for people, but it's best to be thinking about this in terms of, years of operation, because oftentimes, as Chris pointed out, the more expensive devices will pay for themselves over the long run through lower operating costs. And then also, I love this, carbon footprint shot here too, because you can see that it can be vastly different depending on which way you decide to go. So I love this slide. Thanks.
We've got a lot of questions coming in, Christopher. So I think
all right.
So
maybe just final thoughts, and Zach, chime in if you got any additional comments you want to add to this. I think that the main thing I want to point out is that the variable speed heat pumps don't require backup, at least in the more milder climates. You'll still need backup heat if you're in Wisconsin or Montana, and that's pretty important. As Zach pointed out, sizing your equipment is really important because you don't want to overpay for too large of a heat pump. You want the heat pump that's going to serve your house's needs specifically. So I would look for an HVAC contractor that actually does a load-based calculation on at least a zone kind of level or a block load level. The third point is that sometimes the best solution really actually might include fixing your house up a little bit. And this is hard to do if you're dealing with an urgent change. If you're an unexpected failure of your heating system, you're not going to like say, oh, wait a minute, before I get my heat back on, I'm going to insulate my house. That's the kind of thing you have to have a little forethought for. And if your house is built before 1992 in the Northwest, you definitely want to consider having help with from your utility, see if they offer any kind of support for an energy assessment that it might include air sealing, insulation, and window upgrades.
I will jump in on that one to say a lot of times the home improvements that are necessary are pretty obvious when you look. And so a good HVAC contractor will be pointing that out as they go.
Yeah, that's a good point. I'm going to keep going through here and then we'll get to questions. You know, one of the neat things about buying a heat pump ultimately is that as the grid gets greener, your electricity is going to be sourced from greener and greener solutions. And the last point, of course, that I've been making all along is that on balance, variable speed heat pumps cost about the same as their gas furnace with an air conditioner. And so it really comes down to, you know, where you are on sort of that urgent versus forethought kind of scale, and what your personal thoughts are about carbon versus clean. There are a lot of options out there. So with that, I want to thank you, and I'm open to questions.
Right. Well, thank you guys so much. You've such a fantastic presentation, and you've set a record for questions in the Q&A. Thanks, folks. You know, we will, and for this one especially, we are going to put any questions we don't get to in a Google Doc and ask our panelists to look at them, and then we'll send them out to folks. So we'll try to get to all questions. I want to start with our first question in the chat, just to kind of highlight or in the Q&A, excuse me, just to kind of highlight this point that for me has always been super confusing, that when we're talking about central heat pumps, the focus of today's webinar, we have these central systems and then we have ducted mini splits. Can you guys just put one more fine point on that so people understand the difference between those two?
Christopher, you want to have a stab at it first?
Yeah, the joke is that the ducted mini split are sometimes called ducted ductless, which is kind of funny in of itself. But really what it is that the air distribution side on the inside of the house is typically very small with the mini splits. They're little pancake shaped things that slip up above the ceiling in the drop soffit or something like that. They have pretty low airflow rates, and they're designed for 1 or 2 or maybe 3 rooms. Whereas a central forced air system is a whole home, and it's going to deliver 1,000 to 2,000 cubic feet of air per minute, CFM, much larger.
And see, from my perspective, I'm doing a lot of ducted mini split systems for the whole homes where we put a bigger box style air handler on, and it handles it really nicely. A few of the technical differences make a difference on the installation. For the traditional heat pump, the lines, the refrigerant lines connecting indoor and outdoor will be different sizes. So sometimes you have lines buried in walls, and then you want to stay with the traditional versus replacing to the mini split style refrigerant lines that both need to be insulated. And it's a lot more important to pay attention to the refrigerant line sizes. So, you know, some of it is just, you know, differences that your installer should be worrying about, but they might have implications for whether it's a doable option for you.
One of the things I wanted to touch on, there was a kind of a comment / question about the doing these, if you're interested in changing, particularly if you've got a gas system, I would say, and you're interested in going to an all electric system, you know, doing this before your system breaks. So, because I mean, obviously, if you plan ahead, you're going to more likely be able to do this without incurring any downtime where you're not getting heat in there. But do you have any advice, Zach, on when someone might want to think about doing this if their system is still working? So do you kind of do this before you're in that really desperate situation where making a big change is hard to do?
But 2 things come to mind. And one is that people are not doing themselves any favor by eking as much life as they can out of these old gas furnaces. I mean, I go out so frequently where there's some real serious health issues, and the systems they should have been changed long before they died. The second point I'd like to make is that gas furnaces, that whole technology is evolved as well, right? So they're more efficient. The fan motors are using less energy, but they're so much more sensitive to, say, airflow issues. And there are a lot of all the things that I was talking about making sure you're not leaking from your ducts or your building, whatever. If you're going with a traditional system, those would be good things to do too. And you want to be doing variable speed. But a lot of the stuff that might mean extra costs in installation apply to the older systems and bring the costs more on par.
I mean, roughly how old, like if you've got is there a number that's a rule of thumb? Like if you've got a furnace that's older than say 15 years or so, I mean, that's a number I've heard before. This is a good time to might be
So there are
thinking
some
about
really
it.
old furnaces. Yeah, 15 years is a good place. And once a furnace is older than 20 years, then I start to, worry if the heat exchanger is still intact and if people are, if there are some red flags. But
Okay.
yeah.
Well, great. So let's try to get to as many as we can in the next 10 minutes. We might go a couple minutes over. A couple folks, have been really talking about ground source heat pumps. So rather than these air source that are outside your house, but something that's pulling air from the ground. I know we can do a whole nother webinar on that. I want to just, is there a big difference? Is cost the big difference that you guys can see between ground source and these air source heat pumps that we've been talking about today?
There's an enormous difference. The upfront cost of doing groundwork are major. The ground source are a better option in places where you know what the conditions are in the ground. So there are a lot of people that put a lot of money into ground source systems, and you don't know if you're going into rock or clay or water. And so a lot of, if you want to do ground source, then you want people who really know what they're doing. And I see that often they don't do the testing of the ground conditions to know exactly what the results will be. And the air source results are improving so much, so rapidly that we just see fantastic COPs from air source that make it an interesting, people that will be going for ground source, hopefully will be getting into all the details to make that decision.
Great. Brian, do you have a...
There was a one question about, I know there's been a lot of concern about the ETO, Energy Trust of Oregon incentives here. And, actually we've been involved in talking a lot of conversations with them about making sure that the incentives are available for people who are switching from gas to electric. So if you go on the ETO website, they've updated their website. So you'll see now that it's pretty straightforward. It doesn't matter which energy source you're using currently, you will qualify for an incentive for a variable speed heat pump. So I think I know that's an important thing to kind of clear the record on, because there's been a lot of confusion about that here in Oregon.
I've got a good one. If you're, because a couple folks asked about gas boilers going through radiators. So do they have any options, especially in the Northeast, if you're using a gas boiler to a radiator, to replace it with a heat pump?
Yeah, the challenge with gas boiler replacements is the temperature of the working fluid is a lot cooler with a heat pump. So I wouldn't take on that without first making some upgrades to the building so that the amount of heat you need is less. So if you've got a gas boiler currently and you want to switch to a heat pump, you can start off by making the house more energy efficient, and then you can get away with that lower temperature heat pump, and it's a great solution. But if you try to go straight without upgrading your house, you're going to need a really expensive heat pump.
Hydronics, that's a whole nother interesting topic. And there's some really amazing air to water heat pumps and wonderful things if you want to put in a really fancy system, and you can find contractors who really know what they're doing.
Hey, Joe, I've seen a handful of questions about costs. We didn't really actually state costs. And I think it's kind of maybe both Zach and I taking kind of a stab at kind of where costs are. For a single speed heat pump, you're looking at 10 to 12, maybe $13,000 for a pretty simple single speed. For a variable speed, sort of the mild climate ones were in the $12,000 to $15,000 kind of range for a simple pull out the old one, put in the new one, no fixing of the ductwork, no complex routing or anything like that. For a gas furnace with an AC, Zach, do you have a sense of where that kind of typically runs for a project? It's probably kind of on the order of $10,000 to $12,000 for a simple.
Right, 10 to 20, because there's a huge range of
Yeah, I know. I'm going for that kind of low end where the starting point is for people.
Right.
You can always spend more. You can always get your Mercedes or your Bentley if you want it.
Great. Any more to say on the costs?
My
You know,
goodness, there's
there's a
such a
ton.
range.
Okay.
Talk with your contractors.
You know,
But
and
I think it's fair to say, because I've heard, and you guys mentioned it today too, that in general, if you're replacing a gas furnace and an air conditioner, is going to be relatively similar in cost to going to an all electric heat pump solution. But again, there's going to be a lot of variation house to house. But generally speaking, you're kind of in a relatively parity situation with those costs. But if you're just replacing the gas furnace compared to that's cheaper than
Yeah.
putting in a new heat pump, but you won't have cooling. So, that's why all these things are a little bit complicated to do a direct comparison. But I think that's a rule of thumb that I've heard pretty commonly from installers.
Well, one thing to think about is that an air conditioner is a one-directional heat pump. So to take a one-directional heat pump called an air conditioner and upgrade it to a heat pump, which can heat or cool, adds $500 to $1,000 for the equipment. But it's no more complicated to install, so the installation cost is really very minimal. And that would be for, going from a simple air conditioner to a nice quality heat pump.
Yep. There's some good questions here about panel upgrades, and maybe that we should touch on that really quickly, because
that's a good one.
I know that can be an issue with older homes in particular. But any thoughts on that, guys?
Now, if you have an electric furnace or if you have an existing heat pump, there shouldn't be any problem at all. The challenge arises when you have a gas furnace with maybe only 120 volts supplied to that air handler in the garage or location, and suddenly you're wanting to connect a 240 volt, much more high power, all electric system. Then you would need some form of additional electrical work, may trigger a panel upgrade if your panel was on the border as it started.
And so I'm often the one to find that it's time for a panel upgrade, but people, for me, they're often looking to add AC, and I'm introducing them to the idea of a heat pump. And so there's no additional requirements. If you need to do a new, you want to add a heat pump and you want to do backup heat, then that's usually difficult. Backup heat strips. So it's nice to have one device that you can add that covers the load.
I love this question about noise concerns with heat pump HVAC, and I know that's a Zach. We've had a couple of comments just about the noise differences, but do you want to touch on that and maybe compare the noise to air conditioners too, as just another reference point for people?
Oh, absolutely. So a lot of heat pumps, the big cube style is exactly the same as an air conditioner. So usually like 72 decibels. That's a pretty noticeable hum. And if it's happening during the day for cooling, not a big issue. But if it's going, day and night because you rely on it for heating, then it can be a really big issue. So when you have, in a lot of places that are now mandating that people go electric, they have noise ordinances. They'll say like, you have to be under 50 decibels at a property line. So you really want to be looking at side discharge units, and it will be critical that people use those, those mini split heat pumps are going to save the day over and over again because they're wonderfully quiet.
And all this equipment has ratings. So when, if you're being presented with an offer from a contractor, you should be able to ask them for the decibel ratings. And in general, Zach, would you say if you're worried about noise, you should be looking for one that's rated at under 60 dB, wouldn't you say? Something like that?
Absolutely. The ratings can be really frustrating because a lot of times you look in the literature and it will say as low as so many dB. And you have to dig a little deeper to find out what they'll actually, what they can't be.
Great. Well, maybe another question or two. I think you guys are going to really like this one. What type of service provider do I look for to help us evaluate and seal up our home? Who would actually do that work?
That
First
falls
off.
under the rubric of home performance. And
Yeah.
so there are a lot of combination contractors that do that. So basically, contractors who do insulation, they're also going to be thinking about air sealing first, right? One's the windbreaker, and the insulation is then the sweater. And so that's where you would look.
I see that there's this question about using the smaller unit versus the larger one. I think I think it'd be good to just go back to that for just a second, because this really is counterintuitive. This notion that a smaller unit might be better, and
less capacity, not physically smaller. And so that is the idea of a steady wash of, when we're using BTUs as our measure of heat, and a BTU is equivalent of, say, a wooden match that burns all the way down. And so if we're just putting those BTUs into the space evenly, we can condition the space instead of just throwing a bunch of BTUs into a space and putting heat in that satisfies the thermostat, but it doesn't spread evenly through the space. That's where we're looking at the room by room load calculations, and we're looking at airflows. And
I think the way I've heard it described, which makes sense to me, is that if you, with a really big system that's oversized, what's going to happen is it's going to turn on and deliver a blast of heat. Then it's going to have to turn off because it's delivering too much heat. If you've got the appropriate size system, it's going to be going, basically, you want it to almost be running all the time, because what that's doing is moving air through your house, which gives you good air filtration. When you'll notice that, because it'll be definitely a different feeling inside. But also that, like Zach says, the heat is, because the air is moving all the time, you're distributing heat through the whole house. So you're not going to have as many cold spots and hot spots. And so you're going to be more comfortable, a more even temperature typically. So that's why getting the system appropriately sized is really important. And just bigger is better is not the way to be thinking about this. As I think Zach mentioned earlier.
From a comfort standpoint, we're able to warm the surfaces in that space, so that what you're actually feeling is a radiant heat from the surfaces around you.
Great. Well, I think we are a couple minutes over. We have a record number of questions. We will put them in a Google Doc and ask a little more of our time from our fantastic presenters and try to shoot those out for you in a couple days. We'll send the recording of today's webinar tomorrow, along with all the slides, so you can geek out along with us. And I think there's a lot more on this conversation. We are really excited about all the enthusiastic response we've had around it. So that's it from here. Brian, anything else to add?
No, I just want to thank our presenters, Zach and Christopher. Thank you so much for your time and all the preparation you did, and really appreciate it. Thank you for everyone who's tuned in. We hope this was helpful. And if you have further questions about any of your electrification projects, there's tons of information on our website, and Joe and I are both happy to answer questions. Our contact is also on our website. So give us a call, and good luck with all your electrification projects.
Thanks so much, y'all.
Yep. Thanks, everybody.